I want to now go to the next model, which I think is really motivated by looking motivated by looking at the performance of graph algorithms in MapReduce. So people now, it's well known that graph algorithms, even actually Google people are the first probably to notice that MapReduce is not very good for doing algorithms, right? Because this is good, but this is sort of set up in the fashion it has been set up so that I get constant rounds. But you can see that in general it's a very artificial model, because I am basically, so this model is artificial because you can see that the modeling assumptions depend on the input, right? So because I am assuming it's dense and then it is 1 to the n plus epsilon, okay. So for example, if the graph is already sparse, then this does not make sense, right? If the graph is sparse, then I cannot, that means there are only order n edges, right? Then I cannot assume this many number of things, then my memory size will be little of n, because it always should be sublinear. So my model changes with the data, so that is not a good model, that is not a very good model, okay. And you can still do that, but the number of rounds will be much more then, okay. And people also found that in practice that actually MapReduce is not very suitable for algorithms that take lot of iterations, lot of rounds, and many graph algorithms are like that. Whether you take MST, even worse algorithms like breadth first search, shortest paths, they are much more iterative, okay. They take probably diameter rounds or something like that, okay. So they came up with another system called Pregel, okay. So again Google guys,
Is it Pregel?
Pregel, yeah, Pregel, yeah. So now a lot of other systems are based on that, but there's a different, but all these systems that came up, Pregel and other systems that came after this, they are based on a somewhat different paradigm. So basically their paradigm is very close to the distributed computing paradigm that we have seen till now, okay. So there it is what, it's there you have a paradigm which is, so let me go to that. So the paradigm is much more naturally suited for distributed computing, okay. So where you have a bunch of machines, because you have a bunch of machines, the machines cannot change, machines are always fixed, right. I mean you can't change the machines, means the memory based on the input. So if you have like super dense, I can't say the memory is this much, if it is sparse I cannot make the memory smaller and so on. So the machines are machines and they have some memory, whatever, okay. So you have a bunch of machines, let us say you have k machines, that is why it is called the k machine model. It is also called the big data model, okay. So a bunch of k machines, let us say 4 machines here, and they are connected by a network, that means they can communicate with each other. This network is completely transparent, okay. So this in Google will be the data center network, so they compute, okay, they exchange messages. So right now we are simplicity, we are going to assume that it's a complete, that means every machine can talk to any other machine, okay. And you have your data, okay. So the data is there, okay. So maybe it's of size n. So in the graph setting it will be the number of edges plus a number of nodes, okay. That's the size of the input, that is distributed among the machines, okay, because you have to distribute, because obviously overall, although one particular machine cannot hold the full data, overall it should be able to hold them, otherwise you can't do anything, right. So each machine will get approximate, it's a balanced distribution approximately. So each machine will get, this is the basic model, we will come to that a little bit more specific shortly, but this is the whole thing. So they are distributed, there is no memory and all, because I am assuming by default that there is so much memory to hold at least 1 by kth fraction of the input, otherwise I cannot do anything, okay. So each machine has enough memory to hold, so memory is not even an issue here, memory is implicit, because it has to have every machine, there are only k machines that can try to process this data, each machine should have at least 1 by kth fraction of the memory to hold the data, okay. And they jointly process whatever computation you want to do, MST or maybe this sorting problem, this n might be list of values, you want to sort them together, whatever be the problem, your favorite problem, graph problem or a non-graph problem, whatever, and they jointly compute, okay. So that is the model, okay. So here, so this model is, you can see that's quite different from the MapReduce for one thing, because it's not stateless. So this data which is there in this machine is always there. Of course it can get, and so it computes this. So this is very much like, it's exactly like your distributed computing model. So that is basically the model that is inspired by Pregel. So Pregel is false. So this kind of model captures Pregel and other systems that came after that. Okay, Giraffe, and now there's so many systems, Spark. So all these systems are in this setting. Okay, this captures all these settings. Okay, so even MapReduce to a certain extent, but not in that flavor. Okay, so here it doesn't model memory. Memory is implicit. Okay, so there is state. Of course, each machine has its own memory. It has state. For example, if it gets n by k, this state is already there. There is no need to move it around. So it has this initial input, and that input is free for it. It already has this. So only it has to pay for getting messages and things like moving like that. Okay, but this is very much stateful. So every round it's exactly a distributed computing model. So it gets some input, initially the n by k fraction of the input, does some computation, local computation, sends messages, receives messages, and so on. At the end you have to jointly compute something. Let us say MST means, if you look at the overall output of all the k machines, n minus 1 edges should be output. So ideally here I really want to load balance, because you do not want each machine to be a bottleneck. So if there are n minus 1 edges in the MST, ideally I want all the machines to output 1 by k fraction of that. So everybody will output n minus 1 by k edges. Okay, if I allow one machine to do a lot of things, then that is a bottleneck. I want to completely balance the computation and communication, everything. So and let us see an algorithm in the k machine model. Okay, so I am going to design an algorithm in the k machine model, but before that let us look at this paradigm of graph algorithms in the message passing sense, and that sort of motivates this whole model. Okay, so this kind of model is very natural when you try to think, very natural to model graph algorithms, because graph algorithms you can think of them as actually message passing algorithms. Even centralized algorithms you can think of like that, like as I told, in this object oriented way, right. In fact, if you write a code in this completely object oriented sense, you will not treat graph, a node, as an array point in an array, but you treat it as an object. So each node is an object and it computes by sending messages. Okay, those are the methods. Methods is basically sending messages to its neighbors. Okay, so and that is actually the model that was initially the motivation for this Pregel, and also it is exactly like that. Okay, so now, but let us come back to this and let us go a little bit more specific and look at a particular thing. For example, let us say we looked at distributed algorithms. Okay, so you can think of every graph algorithm in the distributed sense. Okay, where, for example, for MST. So in the MST we looked at the distributed algorithm for MST, where each node performs some computation. So but now I am going to think of this model as what I am going to call as, so all the graph algorithms that we have seen till now, like last week, right, you can think of them as vertex centric. What do you mean by that? Think of the graph as a network. Okay, the input graph here, think of this as a network. If the graph were actually a network and you want to compute, let us say MST, that is what you would have done. So each node is a processor and the edge, graph edge, is actually a link, and that is what we did. So you can see that initially it has the same input model. So each processor only has its local knowledge. It means it's the incident, it knows about itself, maybe its ID and its label or whatever, and its incident edges. Okay, and it communicates by sending messages. At the end, every node should know what edges, which of its incident edges belong to the MST, which do not. Okay, so of course this is another way to look at a centralized algorithm in a completely distributed way. Okay, so and in fact distributed algorithms are exactly this. So they are vertex centric, because each vertex you can think of it as a processor, although it's not, it's a kind of a dummy thing, right. If you think of it as an object or a thing, you can think of it as a processor. Okay, that means think of the input graph as a communication network and apply the distributed algorithm, and you will still get the result. Okay, so a distributed algorithm is also a centralized algorithm where you try to sort of simulate it on the thing. Okay, but here it's the vertices are not process, the vertices are dummy, right. So the processor are actually the machines are actually doing the computation. Okay. So, you can try to simulate a vertex centric distributed algorithm in the machine model, where the computation done by a vertex is actually simulated by the machine that has the vertex, right. So, you can take a, suppose I want to solve the MST problem, you look at the distributed MST algorithm, let us say we looked at the GHS algorithm, the pipeline algorithm, the other, the D plus square algorithm, whatever the algorithm you have, they are all distributed algorithms, they are all vertex centric, because they assume that each vertex is a now a process as a processor and the links are the edges are links. I am going to try to simulate that in the K machine setting. Okay. So, this model is machine centric, because the vertices are just dummy, they are just data, right. So, but in the vertex centric model I am pretending the vertices as process, but here they are just data points. The actual computation is done by the machines that are holding the data. Okay. So, this is machine centric. So, the main thing, so one way of implementing algorithms in the K machine model is to take your vertex centric algorithms that we have, that has been known for like 30 years or whatever, we studied that last class, and try to simulate them in the vertex centric fashion. Okay. So, simulate vertex centric algorithm in the K machine. Okay. So, let us do that. So, that gives you, so that immediately gives you a way to write like algorithms in Pregel and Giraffe, because you take your favorite graph problem and take the distributed algorithm for that problem, and you write the code for that as though as the vertex is executing the code. Okay. The machine will take care of that. Of course, if you say this vertex does that, it is not the vertices will do that, seamlessly the machine that has the vertex will do that. Okay. So, that means in the distributed algorithm, if you have, so in the distributed algorithm, this is the, so this is the input graph, but you pretend this input graph as a network. So, it will be sending, so let us say you are computing MST. Okay. So, maybe I am in what happens in the MST computation. So, or in any distributed algorithm, there is always this, each it goes in rounds, receive, compute, send, receive, compute, send. So, I have to simulate every step, every round of the distributed algorithm, the vertex centric distributed algorithm, that is this, the vanilla distributed algorithm we have seen standard in the machine model, the K machine model. Okay. So, that means if the in the vertex centric algorithm, if A sent a message to B, it should be simulated in the K machine. Of course, the local computation is easily simulated, right. If whatever local computation done by A, that machine which has the A will do that computation on A's behalf. Okay. When, and if A sends a message to B, this machine will send a message to B. How will it know where to send? Because it knows the hashing, that is why the hashing is important. So, if in the original vertex centric algorithm, if there is, if that algorithm said send machine, this message to neighbor B, this machine will, the machine that is holding A, it has all the incident edges, that means it will have the A B edge. So, it will look at B, hash the B, and it knows where it is mapped to. Of course, it can do it once, it does not have to do it every time, it has this table of things. So, it knows where B is hashed to send that. Okay. That machine will deliver it to B. Okay. So, that is, so this is a very basic way of simulating. So, let us do this, let us take this, this is the standard way. Okay. That is it. So, what is, so of course, here we know the complexity here, the complexity in the vertex centric, let us say I have any arbitrary algorithm. You can think of MST as a running example, but think of an arbitrary algorithm. So, in the vertex centric thing, what are the communication parameters we were interested in, the complexity measures, the messages and rounds. Okay. So, let us look at that. So, in the vertex centric world, that is that your distributed world, so you add, what are the parameters? You add the message complexity. I am going to denote that as big M, do not get confused, maybe I am using, because that is what we have used. So, big M is the message complexity, small m is the number of messages, small m is the number of edges, sorry, number of edges. So, small m is the number of edges, big M is the message complexity. Okay. T is the number of rounds. Okay. These are two things. Okay. I also need one more complexity measure that we usually did not bother to introduce in when you study distributed algorithms, but it becomes relevant here. and what is that measure? It is this measure, what I am going to call as delta dash. This is the communication so communication, let me call this the communication degree complexity, communication degree. What is that? That is the number of messages that the maximum number of messages that any node sent or received in one round. Okay. So, if you look at it, if you look at this algorithm, it is a bunch of rounds, look at any round, see the number of messages sent by any node and take this over the maximum over all nodes and all rounds. Why is this important? It was not so important in the distributed setting. Why? Because in one it doesn't, because in one round I can send delta messages. I can only send maximum delta because that's the, it has delta neighbors, whatever neighbors, degree neighbors in one round, that's not a problem. But here that's a problem, right? Because if a node has large degree, I have to send lot of messages, okay, through those different links, okay. So that becomes an issue here, okay, because why? Because lot of edges there in the original model, even if this degree is large, I can send, let us say even if this degree is n minus 1, I can send all the n minus 1 messages in one round. There is no congestion because they are all going through different edges. Here different edges are can be mapped to the same link. That is going to cause congestion in this edge, in this link. So I have to look at that complexity also. That might be, of course, that's maximum how much? Delta dash cannot be more than delta. It cannot be more than delta, right? So delta also will come to the picture. It cannot be more than delta, the maximum degree of the graph. Okay, so delta dash will not be more than delta, the max degree. No, in the original algorithm, this is the parameters of the vertex centric algorithm. Okay, that is, so I am just looking at the parameters in the vertex centric algorithm and looking at what is the complexity in the K machine algorithm. But first of all, I did not say what is the complexity metric we are interested in, and that is quite natural. What is the thing that we want to minimize in this model? Number of rounds again, number of rounds, okay. So let me just say it. So we want to minimize the number of rounds. Again in one round, what is the round? Again in one round I can get some messages, receive, compute and send. But of course the thing is there are bandwidth restrictions. If there is no bandwidth restrictions, it is trivial, right? So this whole thing is completely trivial because I can just send all the thing to one machine because I am not even assuming any memory restriction, right? So send all the data to one machine and locally compute it. So everything I can do in one round. Correct, but that is true if you do the random partition, but I am not explicitly assuming any memory thing. So memory is not really a constraint here, okay. Of course if I send that is a very bad because I am going to send a lot of messages. So the real constraint is the bandwidth, or you can think of that either you can put a constraint on the bandwidth or you can put a constraint on the amount of messages a node can receive in one round. So basically a node can receive only about k messages or k minus 1. Okay. So let us put the constraint that in one, just like we had in the vertex centric model, the bandwidth is like polylog or log n. Okay. So I can only send log n bits per message, log n bits of message per round during one link. Why log n? Because at least I have to send the because that's the log n is you need at least log n bits to identify a label of the vertex. N is the size of the input data. So even to send a label A, I need log n bits. Okay, and note that this is quite realistic because the bandwidth is much smaller compared to the input data size. So if input data size is n, the bandwidth is only much smaller, polylogarithmic. Okay, so of course in general you can do this thing with a bandwidth b. You can put as a general parameter, and that b you will always scale it up. So you have to divide by b, but I am not going to divide by log n. Log n is, I am going to just forget about log n factors. So right, we forget constant factors, we are going to forget log n factors. Okay, but in general, if you don't, if you want a specific b, you can put a parameter b as the bandwidth. That means what? You can send. So you'll have a bandwidth. That's the crucial thing. Each link. So that's the other parameter. That's the crucial thing. Each link can allow at most b bits per round. Okay, and typically I am going to assume b to be O of log n or polylog n, okay, because I have to send at least a label typically, just like in the original model. The motivation is the bandwidth is much smaller, that is the whole point, that is why that is models the real life scenario. The links are much smaller capacity than the data that it can carry, that is what creates the bottleneck. So that is why you want to reduce the number of communication rounds. So the goal is simple, so it is a very clean model, number of communication rounds. So if you know parallel computing theory, this is sort of a very simplified version of the BSP model. So the bulk synchronous parallel model, I do not know whether you have seen that, called BSP, bulk synchronous okay. So this is a somewhat complicated model, okay. It was introduced by Valiant, he got the Turing award for that, but still it's a very complicated model. Okay, so people have not developed a theory for that because there are so many parameters in that, there is no real good theory for this, unlike here, because there is only one parameter here. One parameter is just k, the number of machines. Okay. So what do you want to understand, if the k is the only parameter, I want to see, so this is like parallel computing, because I want to see how is the number of rounds scale up with k, because if I increase the number of machines, I presumably want the number of rounds to be reduced, right, that is parallel computing, right. So I want to, if I increase the number, if I throw more machines at it, then I want to get faster, that means the number of rounds should be reduced. Okay. So I want to really study, since we are mathematicians, we want to really study what is the function. So is the number of rounds growing linearly, that means like 1 by k, or quadratically, inverse linearly or inverse quadratically, or inverse whatever function. Okay. So what is the function of k, that is what you want to study. So that will obviously might depend on the problem. Okay. So okay, that is what you want to study. So number of rounds is the complexity measure, okay, and rounds is basically defined the same way that we did before. Number of each round is 1 send, receive, compute, send step, okay, and only I can send limited amount of information. Okay. Okay. So now given this, I want to see how I can translate this. So these are the complexity measures of your classical vertex centric algorithm. So we have studied all these algorithms, broadcast, MST, shortest path, all these algorithms are there. You can think they are distributed algorithms. Okay, so if you had studied centralized algorithms, it will take a little bit of, might take a little bit of conversion to interpret that as vertex centric algorithms, and that is what Pregel does. But if you already studied distributed algorithms, we already interpreted them like that, because we already given them distributed algorithms. We already thought of them as decentralized distributed algorithms. So it is very easy to convert them into this model. Okay. So I am going to now see what is the complexity in this thing, because it is a number of rounds. Here there is only one parameter, the number of rounds. So what I am asking is, if I have an algorithm with this complexity measures in the vertex centric model, what will be the complexity measures in the k machine model? That is the question, I want to answer. So this will be a generic thing. So you take any favorite algorithm or for any favorite problem, you just implement it exactly, you do simulation, the standard simulation, that means whatever local computation you do, the local computation is done simulated by that machine in that round. Okay. So that is free in that thing, here also it is free. Whenever message is sent by a vertex in this machine to a vertex in that machine, it is simulated by sending actually that message. Note that in the original thing I am looking at the congest model, right, it is a congest model. So it also send log n bits, here also I am going to send log n bits. So this is a log n, so it is obviously I am going to look at, so it is important that it is a log n, so congest model. Local means it is completely pointless. So here also one message will be in the congest model, so log n bits, here also I have to simulate it by sending that. But the problem is I might have to simulate multiple things, right. For example, C might be, sorry not C, maybe let us make it, let us see, let us make this red, okay. Okay, and maybe let us make it, yeah, so let us make this red. Okay, so D will also be assigned here. Okay, so D will also be assigned here. So let's say in one step of this algorithm, A is sending a message to B and D is sending a message to G. So G is blue, so G is also, sorry, not G, okay, sorry, let's make this green, okay. Okay, so that means G is assigned to here. So A is here, D is also here, B is here, G is also here. Okay, so in the vertex centric algorithm, maybe it might happen that A is sending a message to B and D is sending a message to G. Both of them have to be simulated across this link, right, because both these edges is sort of across this link, they are mapped to this link, because this simulation A is sending to B and D sending to G have to go through this link. So there is congestion in this link. So if I send too many messages, there is congestion. Okay, so that is going to, so I have to do it in two different rounds now. So in one round I can only send one message, and the next round I have to do it in send the next message.
But the bandwidth is log of capital N, and that's a lot, right? The log of small n.
Log of small n.
Here also it's log.
Yeah, n is the number of nodes.
Capital N is still smaller than log of small n, right?
So what is capital N?
Lesser than small n.
Yeah, data is size n, right? Here it's n or m, baby. So data is n. So here the size of data is the small n, or here m plus n rather, right? But it's still m is n squared. So log of m squared is also log n. That's why I say all. Okay. Okay. But it's not log of k though. It's log of n, because the only k machines. It's not log of k, but log of n. Okay. So now it's really question understanding that. So it's, so to simulate it, so let's see what is the complexity. So I just simulate it in this standard way, right? So I'm going to understand how many rounds it's need. So to just know that, I have to see how many rounds it takes to simulate one round in the vertex centric model. Okay. So let's look at one arbitrary round in the vertex centric model. So in one arbitrary round, some messages are going like that. It's congest. So that means two messages cannot go in the same message, or maybe not more than, maybe one can go like this and one can. So not more than constant number of messages can go through one edge in one round in the vertex centric algorithm. Okay. How many such to simulate that, how many rounds do I need in the k machine model? So now think about this. Now pretend that there is some communication pattern going on in some arbitrary round R. Okay.
On delta prime n by k.
Right. So let's look at it. So m is the message complex, right? Let's write m as, let's split m as following. Okay. So let me erase this. Let's keep this because it's important. So assume this n and m is clear, right? So okay. So m is the total message complexity, right? So let me split this as following. Let me split this as what is this? This is the messages sent by the algorithm in round 1. There are only t rounds. This because message complexity is total messages, right, over all the rounds. Okay. So let's focus on some round. Okay. So let's say some round mr. Okay, some round. Okay, that's the total number of messages sent in that round. I want to see what is the time, what is the number of rounds needed to simulate that in the k machine model. It might be more than one, because there might be this congestion, because two things, although there is no congestion here, there is congestion here, because they are mapped to the same link. Okay. So now to analyze this, let's now pretend that the mapping is done now. Okay. So you have this random vertex partition model, right? So this RVP model. So this is done in the, so what is the random vertex partition model? That gives you this property, every machine has this many number of vertices, every machine has this many, and importantly this is the thing, every number of edges per link is this. Okay. So you you can just pretend that the mapping is done per round, although it is not like that, but you can think of it in the unconditional way, because I am going to take a union mode if you want, or for expectation does not even matter. Okay. So, for expectation what, you just look at it and see the mapping is done now. Okay. So, since the mapping, so every link edges per link is number of edges per link is this, that means what, if there are m edges, every link will get m by k squared plus delta by k, but now I am only focusing on these mr messages, that can be a subset of m, it can be m itself, because these are the total number of messages going across the network. Okay. It can be m itself, that means every edge is used, that means m, but in general it can be a subset of that. Okay. So, think of these edges being, they are all mapped randomly, right, in particular the edges that are sending the messages, they are also mapped randomly. So, how many edges, what will be the number of edges mapped, number of edges that have the active messages going through them in this round, what will be the mapping through each link? It will be exactly this, but instead of m, it will be mr. Because those will be the number of messages mapped. So, I am going to take expectation, in net expectation does not even matter, because I just add them, does not matter, okay, because it is each one of the, because these are, think of them as random variables, you can just add them for expectation. So, I am going to take only the average though. Okay. So, this is these many rounds are needed, because so many edges are mapped to one link. So, I have to take so many rounds in the K machine model, because each I can only send one message per thing, this is only long for just one round. This mr is the number of messages in round r. Okay. So, mr is the number of messages sent in round r. Oh, you are right, you are absolutely right, it should be delta dash, perfect, it is delta dash, not delta, because delta, that is what I said. Of course, the worst case can be delta, but it is actually delta dash, correct, that is why I introduced that, otherwise I would have just said delta. Yes. So, the total, this is the number of rounds needed to simulate one round, number of rounds in K machine model needed to simulate one round of the vertex centric model. Okay. So, what is the total number? Sorry, for all the rounds. So, this will be what? Yeah. So, this will be, I take the sigma inside, so it will be sigma, so 1 by k squared comes out, sigma I is equal to 1 to t mr, that is m, and then delta dash okay. So, that is the complexity. So, this gives you a vanilla way of converting an algorithm in the vertex centric model, that is what we have studied till now in distributed algorithms, to execute in the K machine model. Okay. So, now let us look at a particular problem, okay. So, and then see what it gives you, and can we do slightly better, okay. So, let us look at again our running canonical example. There are a lot, can take any of your favorite problems, graph problems, okay. So, I would say some of the most important problems are MST, shortest paths, page rank, connectivity, things like that, okay. But anyway, let us stick with the MST, because we started with the MST, okay. So, let us say I want to see what is the, I want an MST algorithm in the K machine model, I want to get a complexity for that, one algorithm. So, start with, so you can start with any algorithm with its parameters and then convert it. For example, you can start with the GHS algorithm, which is the vertex centric algorithm, or the pipeline. Different things will give you different complexities, because based on their complexities here, right, whatever their complexities will get translated like using this. So you can call this as the conversion theorem. So this sort of converts that algorithm in a standard way. Okay. Okay, so let's look at MST and let's particularly look at GHS. Okay, we can look at other algorithms as well, but let's look at GHS algorithm first, because it's the first algorithm we studied. So I'm going to implement this algorithm in the K machine model, the big data model, to compute MST. What will be its complexity? So this is one of the first algorithms implemented in Pregel by Google people. Okay. So what will be the algorithm? So what will be the complexity? So I have to look at the corresponding complexity in the GHS. So what is the GHS complexity? What will be M for that? M will be, remember, what is the message complexity of GHS? So it will be M plus n log n. Okay, M is the number of edges, right? So time complexity is what? N log n, and delta dash is what? Can be delta, right, because if you look at GHS, because it the very first thing, it looks at all the neighbors, right. I mean, it can be delta. Because at some point the leader, at some leader might send it to broadcast to all the nodes, so it can be delta. Okay. So let's convert this. If I use this theorem, what will be the conversion? So this is in the vertex centric. So in the K machine, I get what? So I get O of M plus n log n T is okay. So this is yeah. So I'm going to just write it like so. I'm going to omit log factors. Okay. So just to make it cleaner. Okay. So O tilde means I'm going to omit log factors. Okay. So then it's a clean way of stating it. So it will be m by k squared, because these log factors basically go away. M is always at least, m is like n, it's connected, right? M is like, yeah, so almost n log n, right? So you can interpret this based on the parameters. Okay, if it is sparse, so definitely this thing is at least n by k, okay, but it can be much bigger than n by k, right? It can be much bigger, because for example, if m is dense, this will be n squared by k squared. So k, always think of k as so k is definitely little of n. K is much smaller. In practice, like k is like thousands of machines maybe, and n is billions. Okay, but so in practice you can think of, let's say, k is maybe even logarithmic n, but typically let's say, like, you can think of it, say, n to the epsilon, some small epsilon. You can think of it like that. So it's much smaller than the size of the input. Okay, so it's something like so that means if m is n squared, that completely dominates this. So n squared. So if m is dense, this is n squared by k squared.
That also kind of becomes n squared by.
Yeah, if that's n squared by k. In fact, that's even worse actually. Right. So this actually, if it is dense, that means if there are some nodes with degree delta is n, then this is n squared by k. It's very bad. It's reasonable. I mean, it gives you a bound, but it can be bad. Okay. So now let's see whether I can get a better algorithm. Okay, by doing a slightly different, somewhat more efficient simulation, or by sometimes this is the best you can do possible. For example, this is already, if let's say if delta is small, let's say delta is bounded and m is not very large, okay, it's sparse graphs. then this is already very good. I get n by k squared and delta, so n by k, so this dominates, so n by k dominates. Okay, so basically you cannot get better than n by k, okay, but it can be much worse than n by k. Okay, so let us see whether you can get somewhat better than that. So ideally I want to give you an algorithm now that is very clean, that is essentially n by k in all graphs. So this is actually a linear speed up algorithm. Okay, so how will I do that? Okay, so you can also try other algorithms. Other algorithms will be much worse. For example, the GHS, the pipeline algorithm can, because its complexity can be n squared, right. If you look at message complexity comes here, so it can be very bad. Okay, so the GK, the d plus squared of n algorithm, that is also bad here, because although it is d plus squared of n in the vertex centric model, it has less number of rounds, presumably it has lot of messages. So again that plays a role. So in some sense, so this means that I should look at algorithms in the Conjus model that is not only good in one parameter but in sort of both parameters, right. So even if I have a very fast algorithm in the Conjus model but it takes a lot of messages, that is going to take 8 here in the K machine model. So it is very interesting basically. Okay. So now let us see how I can get, so I am claiming that I can do something like this. You can see that is already not given by this vanilla simulation, it may not give this. Okay, so I want to do this regardless of whether the graph is whatever, dense or sparse or degree or whatever. Okay, how will I do that? Okay, so I am going to do a slightly different kind of simulation, and that already sort of addresses a sort of a drawback, a very almost a trivial drawback that was there in the previous simulation. Okay, so now let us look at algorithms in the vertex centric model that where nodes broadcast. There are a lot of distributed algorithms where nodes broadcast, right. So what do you mean by broadcast? Here I should not say broadcast, so I should rather say local broadcast, to contrast with the broadcast problem. Broadcast problem is sending one message to all the nodes, that is not what I am talking about here. So local, what is local broadcast? That means let us say I have a node, in a round a node does local broadcast if it sends the same message, let us say alpha, to all its neighbors. Okay. Of course our model at mode power, it is actually a unicast model, it can, a node can send different messages across different edges in the same thing, that is allowed, but sometimes it might just do broadcast. If an algorithm during all the rounds does only broadcast, then it is a broadcast algorithm. That means all rounds, all nodes are only broadcasting, that means it is always sending the same message to all its neighbors. In fact all wireless algorithms are like that, because there is no edge links there, so you can think of wireless algorithms are doing broadcast, because they only broadcast, everybody who is in the nearby can hear that, there is only one message sent. It cannot send multiple messages because it will be lost in interference, it is only one message. So wireless algorithms are naturally broadcast algorithms. Okay, but you can here also you can think of broadcast in this sense, because if you have links I am sending the same message. Okay, so now let us focus on broadcast algorithms alone. It is not, when I say broadcast, it is not in that sense, it means in this sense. That means every node sends the same message to all its neighbors in all rounds. That means every node sends only one message. Okay. Of course the GHS algorithm, is it a broadcast algorithm? Not in the way I described, because it might be, we will see that you can interpret GHS algorithm in a broadcast way, then that is what gives you this power basically. Okay, so you can interpret GHS algorithm in the broadcast, I will come to that in a second, but that is what I am going to do. Okay, but now let us think of simulating broadcast algorithms. I claim that I can simulate broadcast algorithms better than the simulation that I gave here. Why? Because, so let us say what happens to the broadcast algorithm. So that means the algorithm in the vertex centric model is only doing broadcast, in all rounds all nodes are only doing this broadcast, that means they are sending the same message to all the neighbors. I claim that I can simulate it efficiently. Okay, how? So what happens, let us say this is V, it's sending messages to all its neighbors. Let's say u1, say it has many neighbors, u1, u2, u3, u4, maybe u5, okay, u6. It's only sending alpha to everybody. Okay. So what happens? Look at the K machine model. Okay, u is assigned to some machine. Let's say v is assigned to some other machine. Of course, if they are both assigned to the same machine, that's easy. Okay. No.
You can only send n by k messages on the link.
No. To simulate one round of broadcast for one vertex, how many rounds do I need?
Just one.
One. But in the conversion theorem that I did not exploit that. What I mean is this, right? So let's say, so not uv, I should say u1, okay. So these are the neighbors, right? So u is assigned to, sorry, v is assigned to some machine, this is v, okay. The neighbors are assigned randomly, okay. So they are just assigned randomly. So maybe this machine got 2 neighbors, this got maybe 2 neighbors, this got 2 neighbors, okay. Okay. So what happens in the original simulation? The original simulation, it simulates if you send 2 messages, but they are the same messages. You will send 2 messages here because v sends 2 messages, u1 and u2, okay. Both the messages are sent through this link. So I'll be counting them as 2 messages, but you can do a better simulation, okay. You can just send only one message, okay, and then ask that machine to locally deliver it to u1 and u2. So basically you simulate n by k messages in only one round, okay. So you have to assume a little bit more for this, right, because when you deliver a message, it can't deliver it to u1, u2. That's a lot of information. That's like, I mean, that is bad because I cannot list the vertices, right. When I send v to, I cannot say v send message to u1 and u2. I cannot list them because that's like sending 2 different messages. I will just send v and I will just send message alpha.
But whoever wants to take it with
Correct. So this machine can know the reverse index, right. It knows that u1 v is a neighbor of u1 u2. It should be delivered to that because you can easily have the reverse index. You can already calculate and keep it there. So when it messages, this is the message from v, it knows that u1 u2 are the targets because it knows that they are the neighbors of, okay. So I send you only one message. So I say, so one broadcast can be simulated not in n by k rounds but in one round, okay. Okay. So now let us look at broadcast algorithms. So what is the parameter in broadcast algorithms? There is only 2 parameters, number of broadcasts. Let's look at it. So so you can also look at them, but the time, okay. So there are 2 parameters. One is the number of broadcasts, like there are 3 parameters there. Here the number of broadcasts. What is number of broadcasts? Is the total number of broadcasts done by all the nodes over all the rounds, okay, because every operation is only broadcast. So it's total number of broadcasts in one round by all the nodes, sum up over all the rounds, okay. That's the total number of broadcasts. Let's call it b, that's the parameter, and number of rounds, of course, let's call it tn. There are only 2 parameters for broadcast algorithms: the total number of broadcasts over the course of the algorithm and the number of rounds. In the vertex, this I am looking at the vertex centric model. How long, suppose I want to simulate it in this fashion, slightly more clever fashion, okay. So what will be the complexity in the K machine model? No, B is clear, but you have what? So again look at it in the random vertex partition model. So you have n nodes, they are randomly partitioned. So if let's again look at one round, okay. So let's again look at B you can partition into B1 plus B2 plus BT. That means B1, or where BR generically, BR is the number of broadcasts in round R, okay. So this is the total number of broadcasts in round R by all the nodes, but by random partition again you can argue by expectation that they are randomly distributed. So that means each machine will get simulating how many broadcasts? BR by K. So how many rounds it will take? BR over K, because to simulate one broadcast I need one round, because it has to send to all the links, right, because send it to all the machines. So BR by K is the average, but you can also show that is the maximum, okay, because of the load balancing. On average is BR by K, but you can also show maybe it is 2 BR by K, this, okay, with high probability, okay. So but BR by K is the number of rounds to simulate one round that took BR broadcast, okay. Now I have to sum over okay. So I have to be a little bit careful, so I have to say like this, right, okay, it does not, right. So this is what? So this BR by K plus 1, there should be at least 1, I mean this cannot be smaller, right, this, so this cannot be a fraction, so there is no fractional rounds. So that is why in general it can be B by K plus T, because there has to be at least one broadcast in one round, right. So if I have one broadcast I cannot get 1 by K, that is not possible, I mean I have to simulate at least one, I have to spend that time. So say B by K plus T. So this is an alternate version of the conversion theorem that only applies to, this is you can say conversion theorem part 1 that applies to any algorithm, that it means applies to even unicast algorithms. This only applies to broadcast algorithms. Yeah, this is the number of rounds, B by K plus T rounds. T is the number of rounds, yeah. So T is the number of rounds in the original algorithm, B is the number of broadcasts, that translates to B by K plus T rounds in the, still T is there, still T is there. So this generally assumes that B is not very large. When B is not very large I can do that, okay. So now let me try to solve MST by using a broadcast algorithm. How will I do that? Again I am going to simulate GHS algorithm. But GHS algorithm is a little bit tricky, they are not, it is not really a broadcast algorithm, I did not say it because it is not that broadcast means what, every round, every node should do the same message, okay. So the way we described it, if you think about it, it is not really a broadcast algorithm, but I can think of it, I can implement it as a broadcast algorithm in the following fashion, okay. So let us see this. In fact I think this is one of the questions, this is sort of related to one of the final exam questions, okay. The key is thinking about GHS not in the way we used to think like before, like GHS is operating in a network, but you can think of the GHS algorithm as operating on a clique. That means I have this graph, okay. So what is the graph? So still this is my input graph, right, maybe this is some input graph, okay. So this is my input graph, okay. I am going to find the MST, there are some weights, I did not put the weights, but there are weights, okay. So let me put the weights, I think it is important, let us put the weights. Okay, there are some weights. I am going to simulate the GHS algorithm, but it's what I am going to do to use the GHS algorithm as a broadcast algorithm. I am going to first pretend that the GHS algorithm is actually happening on a clique, okay. So I can think of this edge as this node, this graph as a clique for the purpose of implementing the algorithm. Why? Because when I am trying to do the simulation here, this algorithm is mapped to the network. So every node can communicate with every other node, so even this node can communicate with this node. That does not happen in the original GHS algorithm if you think of it as a vertex, because there is no edge between them, but here I can, right. So I can still communicate, so I can put an edge here between, so I can put a complete graph clique, but of course I have to put a weight here. What weight you should put? Yeah, infinity. So it's, I can use it for communication, but it's not a MST edge, it cannot be a MST edge, okay. So I can pretend that my graph is actually a clique where non edges are infinite weight, but I can use it for communication, Why? Because I can use it for communication in the K machine model. Okay, but if you purely think about it as a vertex centric algorithm, it's not, right. We didn't, that's why we didn't put that. When you have a network, I didn't put links across all edges, because it's not, if it's a vertex centric thing, it's not the case, but here I can. Now I claim that, and this is actually a thing I can implement. Now I am going to study how long it will take to implement the GHS algorithm. What is the GHS algorithm? If you remember, it takes in phases. So there is finding MOE and merge, finding MOE, merge. How many such phases will be there? Log n phases, because we showed that in every phase the number of components is going to be reduced by a factor of 2. Okay. So that's one of the problems in the final. So I asked you to show in the final that you can finish, if it is a clique, I can finish the GHS algorithm in log n rounds. Okay. So you can implement. Why? Because the diameter is 1. The diameter is 1. So to use broadcast. So this is the thing. So you can implement GHS algorithm in a clique. It's a clique here, because I made a clique. Okay. And more importantly, the algorithm is a broadcast algorithm. I can always, this implementation will be a broad, means in every round I will always only broadcast. Why? Because I can show that each phase of the GHS algorithm, which is 2 subphases, first phase is finding MOE, that I can do that by broadcast. Finding, merging them, I can also do by broadcast. You have to think a little bit about that. That's basically your final exam question, how to implement both of them. Okay. So finding MOE, order n, broadcast, finding, merging the components, broadcast. That means all the nodes will send the same message. It might be possible that some node may not send any message, silence, but that's okay, but that's like sending a dummy message, just send a dummy message. Okay. Some nodes might be sending nothing, so just send a dummy message. Okay. So how many broadcasts will be there? So there are order log n phases. No, number of broadcasts, B. Yeah, so time is log n, because there are only log n rounds. Okay, because there are only log n rounds. Okay, and okay, that's also one thing. So I am going to use, so that's why I will do broadcast. So using broadcast, I am going to implement each phase in basically constant number of rounds, like 2 rounds or 3 rounds, constant number of rounds. Okay, so log n rounds, that's what this means, that each phase, that means find MOE, constant number of rounds using broadcast. Okay, find, merge, also same. So both the steps of each phase I can implement in constant number of rounds. That's why I get totally overall log n rounds, because they are only log n phases. This is what you have to think. It's not difficult. You have to think. Okay. How many broadcasts will be there? Since I am doing it so fast, that means each phase constant number of rounds. How many broadcasts will be there? Of course, there cannot be more than n, because only n nodes. So right. So there can only be n. So total number of broadcasts will be n log n, because n broadcasts per phase, order n broadcasts and log n. Okay. So the total number of broadcasts will be order n log n. So if I use this here, if I use this part of the conversion, what will be the complexity of implementing the K machine model? It will be, if I use this with this, then I will get So, I just showed you that I can do it in n by k regardless of the graph parameters. Okay. But this one I did not do, so that is basically a homework thing. So, that is what it is. So, I am asking you how to do, if you have a clique, if a graph is a clique, you can solve the MST problem in log n rounds, because the diameter is so small. Okay. So, in general it is n log n rounds, that is because the diameter is so large, but here the diameter is 1, it is a clique, but still you have to do it carefully because you have to do broadcast. Okay. So, it is much more, there is a more sophisticated algorithm that gives you n by k squared, that I am not going to do. If you come to my seminar tomorrow, you will see that. So, that is much more sophisticated algorithm that does, so actually that is even randomized, this is not really randomized, GHS is a deterministic algorithm. So, you can do it, so the best thing you can do is n by k squared, and that is the best also. In general you cannot do better than this, because you can also show a lower bound. Why? Because you can show that any MST problem you need to exchange basically essentially order n messages. This you can show by communication complexity, but it is also intuitively clear. I mean, n nodes you need to ask, every node should send at least one message. Okay. So, n messages is like sort of a must, and since there are how many links are there, the sort of the maximum amount of parallelism is given by the links, because every link you can send messages in parallel, there are only about k squared links. So, essentially you cannot get better than n by k squared, and you can get that, but that is much better than this. So, that is like a quadratic speed up. So, that is the best possible algorithm you can get. So, that is much more sophisticated. So, that requires very careful load balancing and all. So, any questions? So, any questions on the exam or whatever, I mean, you have any questions on that? So, basically algorithms in this model, I mean, they clearly outperform map reduce algorithms, and the reason for that is I am not moving too many data. The graph that is there is always there, right. Note that in this model, what is a naive algorithm? So, there is a naive baseline, you can solve any problem, let us say for example a graph problem in how many rounds. So, the bounds that we see are non-trivial. So, what is a naive algorithm in this model? I said before, I can collect all the information in one machine and solve that locally, because locally I am not charging for it, right. So, there are basically m information, m edges are there. So, I can send all the m edges to one machine and then solve. So, m by k is trivial lower bound, trivial upper bound. You can see that, that is why I want to, that is why here this is still non-trivial. The earlier thing I had m by k squared, so that is still non-trivial.